Hey you guys, welcome back to another video. Today's lesson I'm going to have to alternate between my laptop and my iPad because there's the calculator app on my computer but not on my iPad. So I just recorded some videos from my MacBook that I'm going to play for you, and then we'll be going back and forth between my videos and me teaching you on the notes. So this is the first video, functions and applications. The idea of modeling, also called regression, is a major component of the AP Precalculus curriculum and will be revisited throughout the course. These topics will utilize the graphing calculators heavily and often include context. In Unit 1, we will work with regression models for polynomial functions, including linear, quadratic, cubic, and quartic, and for rational functions. We're going to review the steps to building regression models on the graphing calculator. This is specifically for the calculator, the TI Nspire. So the first step, once you see, grab your calculator, you're going to press 1 here where it says documents. You're going to select new. And if it asks you to say something, just press no. You don't want to start the process with having something else stored in the calculator. Okay. For step 2, you're going to go to number 4, add list and spreadsheet. Next to A and B, you're going to click this and you're going to type the letter X, and next to B, you're going to type the letter Y. After that, you're going to scroll down to the first cell and you're going to put in data. Okay, you're usually going to be given a table of data. On the notes, I put sample data that we'll just use to practice the steps. So I have -2, -1, 0, -1, 0, 1, and 2. And then I'm going to go back and put the Y values, which are 5, 10, 15, 20, and 25. Okay, now on here, I have listed when you are done, make sure to move the cursor to an empty cell. So when you're done typing, you need to make sure to either move over to the right or move down or just move somewhere else. You do not want to have your data highlighted because for some reason, the Nspire will not pick up that last point. So if your data point is highlighted, it will not be included in the regression model and your answer will be wrong. So it's very important to move over. Okay, from there, you're going to select menu. So over here, you're going to put menu. Then you're going to select 4 statistics and then select 1 stat calculations. Oops. On here, you're going to get a plethora of regression models you can do. Again, we're going to be covering mainly right now, linear, quadratic, cubic, quartic. In the future, we're going to get into the exponential regressions. We're going to do logarithmic regressions. When we get to Unit 3, we'll do sinusoidal regressions and so on. But for now, we're going to focus on the main polynomial functions. Notice that there are 2 linear regression models. They're essentially equivalent. The only thing is that instead of M and B, you're used to seeing Y equals MX plus B. More so in statistics classes, they use A and B instead of M and B, but it is the same thing. The only difference is that the slope M is now represented by the letter B, and the y-intercept that's usually B is represented by the letter A. It doesn't really matter which one you use unless they specifically tell you use this one or the other, and they'll tell you that in the question if it applies. Okay, so let's pick linear regression MX plus B, because what I gave you was a linear model. So I'm going to click linear regression, and then you're going to get this menu. On the X list, you're going to click the arrow and select X. On the Y list, you're going to select Y. Everything else, leave it the same. This F1, you can change it, but just leave it as F1. That'll come in handy later. And then just put OK. Now you're going to get this, so you're going to move over a little bit, and you're going to get the regression equation. So it's mx plus b, and then it gives you the slope that m is 5 and the b is 15. Okay, so then you can write your equation as y equals 5x plus 15. Okay, now let's go on to the next page. Tip number 1. You can see the graph of the regression model by selecting Control Doc after you type the data into the spreadsheet. Okay, so sometimes it's helpful to see what the graph is going to look like. So if they tell you specifically, yes, this is a linear model, yes, this is quadratic, seeing the graph is not that necessary. But sometimes the questions are going to say, what do you think we should use? Should we use a linear model? Should we use a quadratic model? Should we use a cubic model? And then it's like, well, how do I know? So what you can do is go to control. So you're gonna press the control here on top of the equal sign and then select doc. So control doc, and you're gonna get a new menu. In that menu, you're gonna select 5, add data and statistics. You're gonna get these random points. So you're gonna scroll over to this y-axis where it says click to add variable. You're gonna click it. And at the very bottom, you're gonna select Y because that is the y-axis. Then go to the x-axis and select X. And then these points will rearrange themselves. Notice that these do make a straight line because this is a perfect model because of the points that I purposefully chose. They're not always going to be that perfect, but again, it's just an example. After that, you're going to do menu, analyze. You can do regression. And then we did say this was linear mx plus b, so I'm going to click that again. And then you get the equation that we had already got from the spreadsheet, which is y equals 5x plus 15. Okay, and then you can see that the calculator is doing the best fit model. Again, this is the perfect model because of the data I chose. So it won't always be that perfect, but the calculator is basically going to do the best fit line according to the data points that you were given. Okay. Tip number 2, you can quickly find values of functions that are saved in F1. Select Control Doc and select 1, Add Calculator. Okay, so now let's say they ask you, oh, what is the regression equation? You've already done this. You have the regression equation is 5x plus 15. Usually a follow-up question will be, what is the y value when x equals 20 or when x equals 15? Whatever the case is. So then from this menu, you're going to do Control Doc one more time. You're going to get a new menu here. You're going to put 1, Add Calculator. Okay. Now all the Inspires have a keypad at the bottom. On there, you're just going to type F1, and it's going to be in bold now, and then open up a set of parentheses. Let's say I want to know what is the y value when x is 20. So I'm going to put 20 in parentheses and press enter. I get 115. Okay, let's say I want to try another one. When x is 8, it's 55. Okay, when what is x? Sorry, what is y when x is, let's say, -5? It would be -10. So you can use this to quickly evaluate values. Okay, so let's try example 1. The age in weeks and weight in kilograms of 5 randomly selected babies from a particular pediatrician's office are listed in the table above. A linear regression y equals a plus bx can be used to model these data, where y is the predicted weight of a baby in kilograms that is x weeks old. Write the equation of the linear model for these data. Okay, so what we're going to do is go back to home. Now, for some reason, the Nspire does not like it when you keep a data like a spreadsheet in the calculator. You can't just keep adding spreadsheets after spreadsheet after spreadsheet. I don't know why. I've tried it and it just like confuses everything. So just as a good rule of thumb is just delete everything. Always start fresh and go to new. Again, when it asks you to save, put no. Okay, so now we're starting fresh. Again, go to list and spreadsheet. Type X and Y in next to A and B, and now we're going to type in these data points. So all the X values first, 4, 5, 6, 8, and 12. Then I'm going to go back up and type in the Y values. Now you want to be very careful when you're typing because you can easily mess up one number, one little decimal, and any mistake here will make you get the wrong equation at the end. Okay, now important, don't forget to move your cursor from the last data point that you enter. So I'm just going to move down. Again, menu, statistics, stat calculations. Now here they told us specifically a linear regression y equals a plus bx. Okay, that was straight from the question. So I'm going to select the model a plus bx on my calculator. Again, select x. Select Y, leave the F1 alone, and then press OK. And then here is the model. Y equals 3.545 plus 0.185x. Okay, now on the AP test, you need to have a minimum of 3 decimal points. So this is perfect. You have the 3 decimal points. You can have more. If you want to put 4, 5, 7, 10 decimal points, you can. but for no reason whatsoever should you do less than 3. So if you were to round this to 3.5 or 3.55, that would be considered wrong on the AP test. You need 3 decimal points. Okay, so the next question says, using the linear model from part A, what is the predicted weight in kilograms of a baby that is 10 weeks old? Okay, before we answer that question, I actually want to show you the scatter plot. So I'm going to do Control Doc. I'm going to select Data and Statistics. And I'm going to click the Y-axis, select Y. I'm going to click the X-axis and click X. And you can see that on a real table, like with real world data, the points are not going to be perfect. So when I run the regression through this menu on the scatter plot and I put regression and again I put A plus BX, you can see that some of these points are not perfectly on the line. So the point of the regression is to get the best fit line. So the calculator is going to get as close as it can to all of the points, although the points might not be exactly perfectly on the line. So basically that's why it's called the model. So the model is helping us make predictions based on the data that we were given, but it's never going to be perfect. Okay, so again, this is the answer here for letter A. So now let's find the answer for letter B. So I'm going to do Control Doc and I'm going to select Add Calculator. Okay, so they want us to figure out the predicted weight of a baby that is 10 weeks old. So since T, which is our X variable, is the age in weeks, I know that this 10 weeks old is basically the X value. Okay, so I'm going to do F1 and then in parentheses, I'm going to put in 10 and I'm going to press enter. And so the weight of the baby in kilograms is 5.395. Okay. Okay, so back to these notes. Again, so let's write the equation for the linear model. Now, most of the time in real world problems, your variables are not going to be X and Y. So if it is not a real world, like in context, usually this will just say X and Y, and then your equation will be Y equals X, blah, 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 blah. But because the variables are T and W of T, we are not going to use X and Y. Instead, we're going to say W of T is equal to 3.545 plus 0.185 t. Okay, and I write my t's in cursive, kind of like with a little swoop at the end, just to differentiate it from the plus sign because otherwise they look the same. Okay, so just keep in mind anytime you have other variables other than X and Y that you change all of the variables, the calculator will always give you variables X, Y, and you need to manually change it to T and W of T, or it could be H of T for height, A of T for account, or whatever the letter is. Usually the X variable will be T in time. It doesn't always have to be, but you'll see that more often. Okay, so we already calculated the weight of the baby that is 10 weeks old, but these are free response questions, so we are going to have to write a sentence. So remember, to write the sentence, all you do is repeat the question. So I'm going to say, using the linear model, the predicted weight of a baby that is 10 weeks old is, and we had said 5.395 kilograms. Okay, now it's important that you say both the X and the Y variables. So I included the X variable or the T variable, which is 10 weeks, and the W of T variable. And for both of them, I put the units. I put weeks old and I put kilograms. So in real world scenarios, make sure that you include the units. Okay, is it being measured in kilograms, in pounds? Is it weeks or is it years? Is it in billions? Is it in thousands? Is it in dollars? Whatever the real world unit is, include that in your answer as well. Okay. So in this problem, again, they had given us 10 weeks old, which is the value for t. So they said t was equal to 10. Now, on question C, it says the weight of a sixth baby is 5.3 kilograms. Using the model from part A, what is the age in weeks of this baby? So now, instead of giving us the age, they have given us the weight. So that means that W of T is 5.3 kilograms, and we are trying to figure out what is the age in weeks. So we do not know T this time, so we can't solve it the same way that we did it in the calculator when we did F1 of 10. Now this is going to require some algebra skills. Okay, so they gave us the weight, so what I'm going to do is replace the weight W of T with 5.3. So we're going to do 5.3 is 3.545 plus 0.185, and I'm trying to solve for T. Okay, now I got to do PEMDAS backwards, so the first thing I need to do is there anything I can add or subtract? I see this 3.545, which I'm going to subtract on both sides. Now these cancel out. I'm going to go to my calculator, and let's type it in. 5.3 minus 3.545, and I get 1.755. 1.755 is equal to 0.185 T. To get T by itself, I do need to divide, so I'm going to divide both sides by 0.185. Okay, these equal 1, they cancel out. Now I'm going to go back to my calculator, and I'm going to divide my answer by 0.185. Okay, and I get 9.48649. So T is 9.48649 is what we had got, 48649. Okay, but again, this is a real free response question, so we're going to say using the model, we can say let's say using the model, a baby that weighs 5.3 kilograms is about 9.486 weeks old. Okay, so again, I've included both variables, so the weight and the age. Now the age, I did round it to 3 decimal places. If you want to input all of those decimals in your answer, that is okay. Again, just don't put less than 3 decimals. Okay, so they're not always going to tell you what the model that you need to use is. So while some problems will indicate which model should be used, you will also be expected to select an appropriate model type based on a given table of values or by the context of the problem. So example 1, they were nice and they told you we're running a linear regression and here's the equation. They're not always going to do that. Okay, so they might give you just a table with some data and they tell you, well, what is it? Is it linear, quadratic, cubic, quartic? What is it? Okay, so to figure that out for linear models, you're going to have roughly a constant rate of change. Now, if you think about linear functions, we know that they're a straight line. You can have a positive slope like this or a negative slope like that. And if you think about it, all of the y values are going to be either all increasing or all decreasing. So that's kind of how you can tell from a table. Now, you don't want to rely on this because sometimes they'll give you y values that look like they're all increasing or they're all decreasing, but they're only giving you a portion of a graph that could be quadratic or cubic. In those instances, it is helpful to put the data in the calculator and then look at the scatter plot. And then once you see how the points line up, you can tell, does it make a straight line or not? Okay, so if it looks like it's kind of a straight line, then yes, it is linear. So again, that is when the y values are all increasing or all decreasing. Okay, so there is no change in direction. But when usually they're going to ask you to justify why do you think it's linear. You're not going to say because the y values either all increase or all decrease. No, you're going to say I think a linear model is the best fit model because there is roughly a constant rate of change. Okay, now quadratic models, they have roughly linear rates of change and they're roughly symmetric with a single maximum or minimum, and or it could be any context that involves area. Okay, so if you think about quadratics, we know that those are your parabola, so they can open upwards or downwards depending on what the leading coefficient is, depending on what the scenario is. So these, you can see that the y values first half are going down and then now the y values go up, or your y values can start going up and then all of a sudden the y values go down. So the y values are going to change direction but only one time. So the y values change direction once. Okay, they're changing because they're going to either a maximum or a minimum. Okay, so on this one down here you have a minimum, and up here on this one you have a maximum. So if your y values decrease and then increase, you have a minimum, and if they increase and then decrease, you have a maximum. There's a lot of real world scenarios involving quadratic models. For example, it could be, I'm throwing a ball up into the air, something like that, or it can be anything that involves area. So if I ask you to find the area of a fence, or the area of a garden, the area of a picture frame, anything like that. Okay. Cubic models is any context that is involving volume, and cubic graphs look like this, or they could also open the other way depending on what the leading coefficient is. Okay, so you can see that these y values are going to change twice because they go up, and then they go down, and then they go up. Okay, or they could start going down and then go up, and then they're going to go down. So for these, the y values change direction twice. Okay, so that's just something you can think about. Again, it is not always going to be the case. Like if I give you a parabola, but let's say my coordinate points, I'm only giving you data for this half is going to appear that it is all going up. So I don't want you to mistake that for a linear model. Okay, so that's where the scatter plot comes in handy, because you can look at the scatter plot, and if your points look like this, then that's probably going to be a straight line. Okay, but if your points look something like this, then you're like, oh wait, I think that's kind of half of a parabola, so then it has to be quadratic. So you want to look at the scatter plot. It actually will come in handy when you're trying to select an appropriate model type. Okay, so let's do some examples. For example 2, for each of the following situations, determine whether a linear, quadratic, or cubic model would be most appropriate. So A, balloons are filled with water in preparation for an epic water balloon battle. Each water balloon is roughly spherical. The radius of each water balloon is measured relative to the amount of water it holds. Okay, so this is talking about volume, which means that it's going to be a cubic model, right? Volume is 3D shapes. You have your I'm not a geometry teacher, so I'm not good with shapes. But you can think of, filling up a water bottle, filling up a vase, you're filling up a ball with air, anything that's like 3D, like a sphere, a, a vase. I'm sorry, nothing is really coming to mind. Geometry is not my forte. But A is a cubic model. A cubic model would be most appropriate because the context involves volume, right? You are filling those balloons up with water. So you're filling up something with another substance, so with water for the water balloon battle. Okay, Let's look at letter B. Totino's pizzas are on sale at the local grocery store. The price of one pizza varies between $1.99 and $2.19, depending on the variety. The total number of Totino's pizzas are counted relative to the total price of the purchase. Okay, so let's think about when you go to like Domino's or Pizza Hut and you're ordering a pizza. Your cheapest pizza will be a cheese pizza. But the minute you start adding toppings, the price is going to go up. Let's say you want to add pepperoni, you want to add hamburger, you want to add jalapenos, you want to add pineapples, you want to add cheese stuffed crust or whatever. Anything extra that you add is going to increase the price of your pizza. But let's say your base price is the cheese pizza. That's the most basic pizza you can get. So everything is always going to start off with a cheese pizza, unless you're lactose intolerant and you don't eat cheese or something. But for the majority of us, the basic will be a cheese pizza. Okay, let's say a cheese pizza is $5, and then $2 for pepperoni, $1 for pineapple, $1 for jalapenos, etc., etc. Even if you want extra cheese, that's another charge, right? So this is going to be a linear model. So a linear model would be most appropriate because the price depends on the variety and a constant price per topping, right? So just as an example, let's just pretend we know that linear functions are y equals mx plus b, right? So let's say that my cheese pizza costs $5, and then every topping I want to add is going to cost an extra $2, right? And then X will be the number of toppings. So if I put three different toppings, then I'm paying $6, right? 3 times 2 is 6. If I want to add extra cheese, I want to add jalapenos, I want to add pineapples, anything extra that I add, let's just pretend they charge me an extra $2. But this is my base price for just a regular cheese pizza with nothing else on it, okay? So that is a linear model, y equals mx plus b. You have your slope and your starting initial value, okay? Looking at letter C, a sprinkler is placed in a yard to water the grass. The sprinkler rotates in a circular pattern and waters all the grass between the sprinkler head and the furthest distance it reaches. The radius of the circular path is measured relative to the area watered by the sprinkler. Okay, so we're looking, just by looking at the questions, this literally says area. We're talking about the area of a yard. Okay, let's say you have a yard, you have the sprinkler, and it's going around and around and around to water the entire grass that you have in your yard. So that is an area problem. So anything that is area is always going to be a quadratic model. So we're going to say a quadratic model would be most appropriate because the context involves area. Okay. Example 3. The table above provides data for 8 ordered pairs x and y. Which function type best models the data in the table? Linear, quadratic, or cubic? Explain your answer using characteristics from the data in the table. Okay, so let's go back to our little table where we talked about what it could be. Okay, so remember, for linear models, the y values are either going to be all increasing or all decreasing. The quadratic models, they're going to change direction once, and for cubic models, they're going to change direction twice. So let's look here. I'm looking at these y values. We go 5, 10, 15, 17, 18. All of these are increasing, right? They're all going up. But then after this, they start going down, 16, 10, 2. Now they're decreasing, okay? So what that lets me know is that the graph is going to look something like this. They're going to go up, and then they're going to go down, which means that it is quadratic, and there's probably a maximum in the middle, okay? Now with quadratic models, we also said on here they are roughly symmetric with a single maximum or minimum. To find the symmetry, you want to look at the points and see, are any of these about the same? Okay, so usually a perfect parabola, it'll have the same y values on the other side. Okay, but remember, these are not perfect data points, so that's why the word roughly is included in there. So it's going to be as close as being symmetric, but it's not going to be perfect. Okay, so I'm going to look at these points. I see that 10.6 and 10.2 are pretty close. And then if I keep looking, 15.4 and 16.5, they're not that far off if you think about it. 17.1 and 18 are not that far off. And 2.8 and 5, they're kind of close as well. Okay, so what that means is that if they're going to be roughly symmetric and I were to fold this table in half, that means that the center would have to be somewhere in here. Okay, now it's not always going to be in between two values. Okay, so let's say, just as an example, let's say this was not here, and then let's say these were symmetric, let's say these were symmetric, and let's say these were symmetric. Then the one that's in the middle, it would just be a singular point. So then the maximum or the minimum would be at the x value 1.2. But because this problem has an even number of coordinate points, our maximum is going to have to be in the middle of these two, somewhere in the middle of these two x values, 1.2 and 1.7. Okay, so this is how we're going to explain the answer. We're going to say a quadratic function best models the data in the table because the y values increase to a maximum, then decrease somewhere between the x values 1.2 and 1.7. Additionally, we're going to add the y values are roughly symmetric about the x value between 1.2 and 1.7. Okay, now some keynotes. It is important that you specify y values. Okay, don't just say because they increase and then decrease. On the AP test, you have to be very specific. You cannot use they. They're going to be like, what is they? Who are you talking about? Okay, so because the y values are increasing, the y values are roughly symmetric. If this was a real world problem and we had t and w of t, like the other example we did, then you would say because the w of t values are increasing, the w of t values are roughly symmetric. And then you're going to say the t values between 1.2 and 1.7. So just change the variables to what they are in the table that you were given. And again, it's not always going to be, you're not always going to have this somewhere between x values 1.2 and 1.7. Again, just for the sake of the demonstration, if this was not here and the middle point was 1.2, then you would just say they would decrease about x equals 1.2, and you wouldn't put any of this. And you would say the y values are roughly symmetric about the x value 1.2 and none of this. So if you have an odd number of points on your table, or if you have a specific like actual center point that is not in between 2 points, it is okay to put just that 1 point. So it just depends on the table. Again, if you have an even number of points or an odd number of points. Okay, so for the regression, I recorded this on my laptop, so let me go find the video so I can play it for you. Example 3. Now I'm alternating between my laptop and my iPad, so we should have already answered this. We have already discussed why this is a quadratic model. So now we're going to be answering B, which is to write the equation of the regression model. So what I'm going to do is go back to home. I'm going to select one new document. I'm going to select no, I do not want to save anything. And I'm going to repeat the process of entering my data into the spreadsheet. I'm going to type X and Y next to A and B. And I'm going to do the X values first. 0.9, 1.2, 1.7, 2.2, 2.9, and 3.4. Again, you want to be careful that you are being detail oriented, that you're not messing up any of the numbers by accident or forgetting one of the decimals. 17.1, 18, 16.5, 10.2, and 2.8. Again, reminder, you want to move this last cell. You don't want it to be highlighted. You need it to be on an empty cell before you run your regression. Then I'm going to do menu, statistics, stat calculations, and then we're going to select quadratic. Okay, select X, select Y, and press OK. Now you're going to want to move over and scroll up a bit so you can see the equation for quadratic is ax squared plus bx plus c. So they give you the a, b, and c that you need to enter. Now on the calculator, you get quite a few decimals. If you ever wanted more, you can see them at the screen at the bottom. You see you have all of these decimals here at the bottom. You just need 3, so you can just do 4.883. You don't need all of them, although you can do more if you want, but no less than 3. Okay, what we're going to do now is look at the scatter plot by selecting Control Doc and then add data and statistics. Select Y on the y-axis and X on the x-axis, and you can see you get that parabola. And if you run the regression again, analyze regression and then quadratic, it gives you the equation here already, so you don't have to look at the A, B, and C like on the spreadsheet. This one puts it together for you, which is really nice. So yeah. Okay, so let's write the equation. So this is not a real world problem. Notice that the variables are x and y, so I'm going to be able to just copy them straight from the calculator. So we have y equals negative 4.883 x squared plus 15.958x plus 4.995. Okay, there is another video I recorded, 2 videos actually that I recorded that I want to show you. If in your school or when you're at home, you do not have access to a TI Inspire, you can use Desmos to do regression. So what you do is start off by going to a graphing calculator and using your keyboard, you're going to write the word table. Okay, you're going to get the subscripts x sub 1 and y sub 1 in, and then you just type the data. So 4, 5, 6, 8, 12, 4.2, 4.4, 4.8, 5.1, and 5.7. Okay, from there, you can select zoom fit so you can see the data, how it's supposed to be seen. And then you're going to do y sub 1. So to do that, all you do is type y1 and it'll automatically put the little subscript for you. Now you don't want to put equals. What you're going to do is type tilde, which is next to the number 1 on your keyboard, and it looks like this little squiggly line. And then from there, since this was a linear model, we are going to write a, which is what they said in the question, a plus b, but instead of just x, you need to put x sub 1 because that was the variable that we entered in our table, x sub 1. And then you're going to get the formula over here, your a value and your b value. So then what you could do is do f of x is equal to, and you're going to type in a, which is 3.545 plus 0.185x. Okay, and you're going to see that this black line, so if I get rid of the red one, the black line is the one that we got from the regression, and the red line overlaps because it is the same equation, just that I have now plugged in the a and the b that were supposed to be in the formula. Okay, now you can use this to evaluate values. So for example, on letter B, when they said what is the predicted weight of a baby that is 10 weeks old? Now I can do f of 10, and it's going to tell me the weight, which is 5.395 kilograms. Okay. Another example using Desmos. So if you're at home doing your homework, so again, you start off by going to the graphing calculator and you enter table. You just type it with your keyboard, and then you start entering your data points. So 0, 0 0.4, 0 0.9, 1.2, 1.7, 2.2, 2.9, and 3.4. Now we'll put the y values: 5, 10.6, 15.4, 17.1, 18, 16.5, 10.2, and 2.8. Okay, and you can press this little magnifying glass so you can see how the graph, how the points go. And now we did already talk about why this is a quadratic table, why it's best modeled by a quadratic function. So you're going to do y1, you're going to press tilde, which is next to the number 1, and then you're going to type in the standard form for a quadratic, which is ax squared. But remember, instead of just x, you need to put x1 because our variable here is x sub 1. So x squared plus b x, again, x sub 1 plus c. And now you get this equation, which I can retype, which would be f of x is equal to negative 4.88317 squared plus 15.958x plus 4.99564. Okay, and you can see that they overlap because again, it is the same equation. I have just taken the regression model in blue and I have entered the values of A, B, and C. Okay, and now you can use this to make predictions. So if I say what is f of 0.4, we get 10.597, which if you look at the table, it's pretty close because the actual value was 10.6. And our model is predicting 10.59, which does round to 10.6. Okay? Okay, so that's how you can do this on Desmos. Let's go to the last page. I have another video that I recorded for that one. Residuals. We're going to talk about residuals. This is going to be covered in way more detail when you get to topic 2.6. When we use a model to predict values, we expect our model to produce values that are reasonably close to the actual values, but our models are not expected to result in exact values generally. The difference between an actual value and the value predicted by a model is called a residual. So residuals, the formula is equal to the actual value minus the predicted value. Okay, so the actual value comes from your question. Your predicted value is from your regression model. Okay, so let's do example 4. Using the model from example 1, what is the residual of the baby that is 5 weeks old? Interpret the meaning of this value in the context of this problem. Okay, so I'm going to go to home, new, do not save, add list in spreadsheet, type X and Y, type the data, 4, 5, 6, 8, and 12, scroll back up, type the Y values, 4.2, 4.4, 4.8, 5.1, and 5.7. Move your cell to an empty cell, and then press menu for stat calculations, and then X, and then Y, and then press OK. And then now you have this. Now remember, this model is now saved under F1. So what we're going to do is do Control Doc. We're going to add a calculator. Now the actual value is the one that comes from the table. So at 5 weeks, the table tells me that at 5 weeks, the actual weight is 4.4 kilograms. Now let's see what our model is going to predict. So again, type F1, so go down to the keyboard, type F1, and then in parentheses, we're going to put 5. We're looking for a baby that is 5 weeks old, and our predicted weight is 4.47 kilograms. So now to find the actual residual model, you're going to subtract the actual value. So the actual value was 4.4, and you're going to want to subtract that from the predicted value. Okay. Now, when you're doing these regression models, it is important that you copy and paste values that you previously had calculated. This one is only 2 decimals, so it's not that bad. But if you have a repeating decimal where you have a lot of numbers, you're going to want to make sure you copy and paste. You never want to round in the middle of the problem. If you do round in the middle of the problem, your final answer will be wrong. Okay, so it's important that you know how to copy and paste. So some of you guys have already been using Nspire, so you know that if you scroll up and you highlight the answer and you press enter, it'll duplicate it for you. Now that's easy if what you want is right above or it's not too far away from where you need it, okay? So that's one option to copy and paste. Another option would be to highlight what you are trying to copy, and then you're going to do Control C. So just how you do it on a computer, okay? You press Control over here, Control C, and then when you need it, you can do Control V, and it'll paste it for you. So you can do Control C, Control V, just like you would on a regular computer. Okay, so those are two options for you to enter data that you have previously calculated that has a lot of decimals. Okay, do not round in the middle of the problem. Okay, anyway, so back to finding the residual, we're going to do 4.4, which is the actual value, minus the 4.47, which was the predicted value. When you press enter, we get negative 0.07. So that is the value of the residual for 5 weeks. Okay, so let's go ahead and put what I said in the video on here. So again, the actual value comes from your question. So it can be presented in different ways. It could be in the table. They could give it to you in words, like in the sentence, or it could be on a graph. We haven't seen any graphs yet, but they will in the future show you some graphs, and you just look at the graph. The predicted value comes from your regression model. Okay, so that's when you're gonna be typing F1 and then a number in there. So that's how you get the predicted value. Okay, so again, when we were looking here for a baby that is 5 weeks old, the actual value comes from the question. They gave us a table. On my table at 5 weeks, the actual weight was 4.4, and the predicted weight that we got was 4.47. We just did that on the calculator. To get the residual, we did 4.4 minus 4.47, and we got negative 0.07. Okay, so now to interpret it, notice that the predicted weight is more. It's not that far off, but it is 0.07 more. So we're going to say the model overestimated the actual value because the predicted value is larger than the actual value. Okay, so you could have an over or an underestimation. So let's say, just as an example, let's say this had been 4.48 and the predicted was 4.47. Well, now the actual is bigger. So then you would say it underestimated because the actual value is larger than the predicted value. Okay, so just graphically, what the residual is doing. So you know how we did the scatter plot and we had points that look like this, right? And then the calculator is doing the best fit line. What the residual is saying is how far off from the line is your point, right? Because let's say this right here is the actual data. And then on the graph at this same y value, this would be the predicted. So it's how far away the actual point is from the best fit line that the regression model is doing. So just visually, that's what's happening. because again, the actual values are not always exactly on the best fit line that the regression is creating for us. So it's just how far away are you? Um, so yeah, I hope this lesson made sense. If you guys have any questions, please let me know in the comments, and I'll see you guys in the next video. Bye.